Okay, let's begin lecture. You guys ready? Okay. Shh, 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 shh. Just to give you advance notice, I'm going to give you fairly simple homework this weekend. Just start reading chapter 5. You guys have been working really hard on homework lately, so that'll be your main homework. Just start skimming through there and stuff. And we'll actually get to talk about some chapter 5 concepts today. A couple things I want to go over with you, and that is this is actually the halfway point in the semester. Amazing. It's gone by really fast every semester. Just when I start to know you guys, it's over. But that's the way life is. I want to show you something that's in your grades page. For those of you that said, yes, I would like to get the PDF of my Scantron results. That was homework 00. Right now, if you answered yes to that, I've got you on the list. And for about half of the people that answered yes in this section, I've already sent the Scantron results PDF. So let me show you how that works. What you do is you go into the grades page and you go down to the Scantron, the exam 1 Scantron line, and you'll see down there a little icon, and it looks like kind of a text message icon. There it is. A little blow up action there. And to get your PDF, if you don't have a PDF, you won't see that. All right. But if you have it, it'll look like this. You'll click on it. Oh, and by the way, if you don't have it now, because I haven't done everybody yet. I'm still in the first half of the alphabet with you guys. But if you have it, you have a little blue dot next to the grades tab in the navigation menu in web courses. If you don't have it, you will have a little blue dot to signify that you got some new data in your grades page. All right. So then when you do, you click on it. And then what that does is it pops out like this little sub window, like this, kind of blue colored. And this blue colored sub window, if you look at it, you'll see that there's a link to download your Scantron results PDF. All right, so that's what it. So here's an example of it. So there's a text message that says something like, here's your exam 1 Scantron results PDF or something like that. Okay, and then a link. And so here it is again. And all you got to do is click that and it'll download. All right. Now, if you haven't asked for it, you blew it. Okay, you can get it, but you have to come to office hours. All right. And we'll get it for you in office hours. If you want it, we'll have, after exam 2, I'll have another homework 000, and you'll again specify whether you want your exam Scantron results PDF. Anyway, so you do this, you click it, and when you download it, it's going to look something like this. And we've gone through this before. It tells you what number question your answer was. Is it correct or not? Which letter you bubbled in, and which letter was the correct answer. All right, and so you'll be able to use that to see which actual questions. So this is a little bit better than having just the score. The score is on this printout up in the upper right. But if you want to know which questions you messed up on, this printout will help you with that. And for about half of this class that asked for it, I've got them out to you. Raise your hand if you've already looked at yours. Anybody? Okay, good. A few of you. Good. Good. All right. Now, with that PDF, and the blurb file. Now, your guys' blurb files, I still haven't gotten them up. I'll try to do that today. It just requires me to scan them in from the photocopy machine and then post them as PDF. But I'll do that, and you'll have a blurb sheet, and it'll say exam form A, B, C, or D, whichever one you have, and then you look up your blurb file, and that's a PDF. And what that will give you is a short little blurb about each question on the test, except for the matching. But you already know what the matching is about anyways. It's about formulas. But for the true, false, the multiple choice, you'll have little blurbs. So it might say Newton's third law applied to gravity or something like that. If you want to look at the actual question instead of the blurb file, you may do that in office hours. And my office hours, as always, this semester, 11 to 1 on Wednesdays. Okay? And it's normal. Students come in all the time and look at their exam, and they actually look at the exam paper. And the rules of engagement are simple. You may make notes on the exam questions, but you may not copy them verbatim. Okay? So you could go in a little bit more detail than the blurb file. That's fine, but you may not copy them verbatim. All right? And I'll have one of each test form ready for you, and you can just come in and look at it and bring your Scantron results PDF, print it out, and you're good to go. And it makes a nice little study guide, like a mini study guide to go into the final. And so, and you don't have to do it, in the next, 30 seconds. There's no deadline on it. If you want to do it, try to get it done and squared away before the final, before you get into finals week. So by Thanksgiving, you should have all this stuff squared away. Now, let me pause for questions. You were over there last session. No, the guy behind you, not you. What's your name again? Mike? Okay, good. Now, I try to keep an eye on you guys, like where you sit and stuff like that. All right, let's keep going. Another thing that I developed yesterday is have your clickers ready. We're going to do a clicker question in a second. I made a new talking PDF of a big free fall energy table. And I set it up. I put it in, yesterday afternoon. I don't know if you guys took a look at it yet or not, but it's, here's what it kind of looks like. Here's the top, 30%. And it's basically a free fall energy table, plus it has the V squared column, which we didn't do the other day, but which I show you how to do in the talking PDF, and then the V column. So let me get my cursor over here. So here's the V squared column, and here's the V column. And I set it up for a box of Doritos, mass 1.72 kilograms. I looked it up on the internets, and that's the actual mass of a big master box of Doritos. And then I just dropped it from 12 meters. So, and my table goes meter for meter. Now you could do a table every 2 meters if you want, or every 10 centimeters, whatever your delta Y that you want to do from table to table. And then we figured out the top row, got GPE, and then kinetic energy was 0 because it's dropping from rest. And then total energy. And then, of course, V squared and V are zeros up here. And I showed you, I did a full calculation down at Y equals 3 meters. I think it's the one. And so you'll be able to follow the discussion in this talking PDF. And I left a bunch of rows in the table undone so that you could fill those out yourself. And come to office hours and talk them over with me, talk them over with your friends. And, if you're sitting in lecture and, you're sitting next to somebody and you're not friends with them yet, make friends. And so you can have a friend that studies with you. It's always a good idea. And so you study with, so there's all kinds of lines that you can fill in. And let me just emphasize one thing about this talking PDF. And it's good if you make a note of it. There is a pattern between one row and the next. Every row fits into a pattern. And why is that? Because every row has an increment of 1 meter. And remember, the concept with energy is meters and joules interchange. So meter by meter, if you have equal increments of meters, you're going to have equal increments of GPE and kinetic energy. Now, the thing that you're not going to have equal increments for is the energy column, and that's why you can see ditto marks. I figured out the total mechanical energy up there at 12 meters, and then I just put ditto marks all the way down. All right, so that's a pattern, but it's not the same pattern of meter for meter, equal changes. But you're going to see equal changes in kinetic, equal changes in potential, and also you're going to see equal increments in the V squared column. So make a note of that. It's a talking PDF where I walk you through 2 or 3 rows, and you're going to fill in the other rows, and you're going to know your rows are righteous if they fit the pattern, and you should be able to see the pattern. All right? And actually, we're going to talk about patterns in altitude here today. Now, I have an iClicker question for you. Let me get it started. And this iClicker question on frequency DD is just a survey question, so I'm going to mark both of these answers correct. Just give me what you got. Have you used it yet? Have you listened to it yet? Or no, you have not? Just give me what you got. And I've now marked both of these correct. So, and yes, similar to the morning section, the early section. All right, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now, you see these guys coming in late. They didn't get a click in on this question. And that's another way that you can miss getting answers. Let me just review one other thing about not getting answers. And if you have a really low, I was going to ask this or point this out to you earlier. If you have a really low value in the decimals part of your clicking roundup figure, for this class it should be something 0.22. That's the max that you can have, something 0.22. But if you have something like 0.07 and you haven't missed lecture, which and I've had a few students say, Dr. B, I haven't missed any lectures, but I'm down here at 0.07 or, something 0.07. Why is that? The reason is, you might be coming in a little bit late, like, the people the last few minutes, And miss one or two questions. I've been using a lot of questions at the beginning of class. The other thing is sitting in the back. Now, I talked about this Tuesday, and we had a couple guys after class on Tuesday. I see you're up a little further now. And we just did it, we dismissed early, a few minutes early on Tuesday. And I just had the three guys down here sit in the front row, and we did a little mini session, no questions, but just to see if they can click. I can see how many people click. And when they were sitting up in the front, the three amigos, 3 clicks, no problem. And then one of the guys that had the troublous clicker went all the way to the back where he used to sit. And we did another question. So I just tell him, type in any letter, and I only got 2 clicks. And then I said, all right, let's do one more question, and I want you to walk down. Young man with the suit. What's your name again? Yeah. Matt? Matt, raise your hand. He was at about Matt's position on the aisle, and I got his click. I got 3 clicks from there, and he's now sitting right about that. That particular student is sitting about right near Matt's aisle, or Matt's row. So you guys in the back, I said it Tuesday, and I'm saying it again. If you don't do something about it, if you want to sit back there, you're perfectly welcome to, but don't come crying to me about I don't have any answers. I'm not getting any points, and the student that had the it's supposed to work a lot further than that, but it was a little bit stinky, and he rented it from Textbook Solutions, which who knows, who had it before him. But it might have been a used clicker, and so it might have been used and abused and not working very good anymore. So take that into account. If you have a new clicker, always put in new batteries, Energizers or Duracells or something, because otherwise you're going to be SOL. So you guys in the back row, you've been warned. All right, let's try some more free fall energy calculations. You're going to be calculating kinetic energy, but not on Earth. You're going to be calculating on the surface of the moon. Now, the mass of the moon is about 1.23% of Earth's mass. So not as many kilograms, and it's smaller. Its radius is about 0.275, so that's 27.25% of the radius or the diameter of Earth. So it's smaller, and it's not as much mass. And so gravity's a little bit weaker at the surface. All right, so there it is, negative 1.62 meter per second square. Now, here on Earth, negative 9.8. From the top of Mount Everest all the way to the bottom of the Pacific Ocean in the Mariana Trench. All right, 9.8, pretty close, although, because it's only a few kilometers variation. All right, but up on the moon, it's really weak. And that is why, as I've mentioned before, the Apollo astronauts, you look at the movies of the Apollo astronauts, they jump around like deer up there. They can leap like a deer up there on the moon. Now, we're not going to calculate potential energy and kinetic energy of an astronaut. We're going to calculate potential and kinetic energy of a hammer. So write down hammer that is, this is from Home Depot or whatever. I looked it up. Mass 0.703 kilograms. All right, and we're going to drop this on the surface of the moon and figure out some kinetic energy and potential energy and stuff. All right, so your factors here that you want to make sure you have written down: the G on the moon, negative 1.62 meters per second squared, and the mass of the hammer. Sador, question. This one? Oops, I blooped it. Negative 1.62 meters per second squared. So make sure you write that one down. Because, we're going to do, the kinetic energy of the hammer on Earth is going to be bigger because gravity's stronger here. And it's going to fall on the surface of the moon, but it won't develop quite as much kinetic energy, meter for meter, because it's gravity's weaker up there. All right, so here's my hammer. All right, now multiple choice. Let me switch over here to multiple choice. So this one, I'll hit your refresh key. And let's just do a real basic one. What's the weight force of this hammer on the moon? And notice that I've got minus signs here. So multiple choice, A, B, C, or D. All right. Yeah, so do a calculation there. "25 seconds. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you got this one right. A few of you got blazed up on this one. If you bloop this one up, here's the calculation. It's just W equals mg. And so the mass of the hammer is 0.703 kilograms. And G on the moon is kind of wimpy, negative 1.62 meters per second squared. And kilogram meters per second squared, that's a Newton. All right. Now we're going to be doing some Newton meters here in just a second. Because we're going to do... we're going to take this hammer and drop it from a certain elevation above the surface of the moon. So let's do a little review or recall of potential energy and kinetic energy concepts. If you set the baseline, i.e. y equals 0 for your vertical axis in free fall, you can then figure out GPE for any height. So on the surface of the moon, Desiree, the logical place to make y equals 0 is the actual surface. But now think about this room. I could put y equals 0 and if I want to orient to the top of the stage here. That would be logical. And then this elevation where my hand is, that would be about 2 meters positive. But then the floor below the stage would be like negative 1 meter or so. Negative 0.8 meters. All right. Now, the other thing that I could do in this room is, all right, I don't want y equals 0 on the stage. I want y equals 0 on the floor in front. That's a logical place to put it. But on the moon, y equals 0, the surface of the moon, that's probably the best. All right. Now, with that, you can calculate GPE at any height because the formula is a little bit cinchy. If you make, the range of motion with y equals 0 at the very bottom, then all the delta y's are positive on the way up and negative on the way down. So GPE just becomes a little bit simpler notation-wise, minus mgy. All right, and you can calculate GPE at any point on the moon. Now, here's a picture of an astronaut backing out of the lunar module. Can you imagine the thrill? I mean, man, I love that photo. You know, the commander, the mission commander's already on the ground. You know how you can tell? He's the second man out of the lunar module. Somebody's taking the photo. Yeah. So, anyways, you can calculate GPE, and then you can, if you know the kinetic energy at any level. So, for instance, the top of the motion, or maybe the bottom of the motion, or any intermediate height, then you can figure out the total mechanical energy, E. And then once you got that, you can figure out everything at any level. Because remember, once you get E, at any level in that column, you could put ditto marks all the way down and all the way up. You know, everywhere on that column. You know, so if your total mechanical energy is 5.7 joules, just put 5.7 joules in one of the cells of that column, and then ditto marks above and below it, and ding, you're done. And then you do subtractions. Then figure out GPE, subtract that from the total mechanical energy, and then you got your kinetic. Then your kinetic energy, you got 1/2 mv squared. You can figure out what v squared is. And then you hit the square root key, you can figure out what v. So you can figure out everything. Once you get E, you can get all these other things. Kinetic energy and downward speed. Or upward speed, for that matter, if it's on the way up. Because on the way up, it's going to, at height 2 meters above the lunar surface, it's going to have a certain speed going up, and it's going to have the same speed on the way down at a height of 2 meters. So, now, let me pause for questions because we're about to do a calculation. Do you have everything written down? Okay. All right, now we're going to do a calculation, and let me get the calculation set up. So I want you to hit the refresh key. Here's your calculation. The astronaut drops the hammer from the small platform on the lunar module from a height of 2.2 meters above the surface of the moon. What is this kinetic energy halfway down at height 1.1 meter? All right, so your table, your free fall energy table, 2.2 meters is the top, 1.1 meters is middle row, and then 0 meters, you don't have to do the 0 meters, but I mean, that would be the bottom row. So go ahead and do that. And consult with your neighbors, and I'll give you a couple minutes to figure this one out. Because this one's like doing 2 different rows of the free fall energy table. And don't forget, this is on the moon, so 1.62 meters per second squared, et cetera, et cetera. So go ahead and do that, and So double check with the people around you. Whoever's sitting in front of you, whoever's sitting behind you. Be neighborly. And actually, the multiple choice question was part of this set of calculations. Good. I'm glad I see you guys double checking with each other and stuff. It's good. All right, 1 minute. Thirty seconds. Excuse me. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Raise your hand if you typed in 1.253. Nice. Okay, look around you. Wait a minute. Put your hands up again if you typed in one. Look around and see if you see anybody that got it right. Hold your hands up. Keep them up. Look the other direction. Look around you. Look, hold them up high. Hold up your hands high. Come on, so that everybody can. Okay, good. All right. Now, that person that you saw holding up their hand, you can put it down now. Okay. They are geniuses for today. So that's good. Now, I want to show you the answers, something that I discovered first hour. It's not very important, but here are the answers. Here's the correct answer. Now, everybody typed in 1.253, but you know what my computer registered it as? 1.25299999. And so that's, I was looking at that this morning in the 9 o'clock section. I thought, why are they doing that? 7 digits? I only want to 3 decimal places. But what happens is a computer, like your clicker, it's digital. That means all its numbers are represented with the binary number system, which has 2 numerals in it, 0 and 1. And you can represent any number you want, but sometimes when you convert it back from digital to decimal like this, it bloops up like this. Now there's probably at least another. See, look here, 1.25499999. That's another one. All right. Now, I want you to look at this one down here, negative 1.253. No, N-O. The numeric part is right, but kinetic energy is negative, never negatory. So there's only 2 people type that in. Make a note to yourself, no, you got the right number, but it shouldn't be negative. All right. Now, potential energy can be negative or positive, but not kinetic energy. All right. So some of these, so here's another negative, and they rounded it off correctly. Here's somebody that misplaced their decimal point. Here's somebody 0.0254. I don't know. Negative 2.886. 1.26. See, these are rounded off incorrectly. And I'll be grading for that. So make sure you take my advice about that. Now, I'm going to give you one more answer here. The downward speed at 1.1. Go ahead and write that down. 1.89 meters per second. And if you look at the talking PDF that I put together for you yesterday, it's up in web courses on the talking PDF page. You'll see how to get v squared and then v. All right, so I'll write this down, and you go ahead and write it down, then you can re-verify that later as a study exercise. Matter of fact, filling out the entire rest of the table on the talking PDF in your notebook is a good study exercise as well. Now, why do I say that? Because exam 2 is coming up. And you do not know what's on exam 2. And I do not know what's on exam 2 yet. But I kind of know what's going to be on exam 2. And for that reason, I know that if you use the talking PDF and really know it front to back, top to bottom, wall to wall, you're going to be happy on exam day. I'll just put it that way. All right? And so fill out those lines. Now, here's the calculation, in case you got tripped up on it, which a few of you did. Minus mgy. And so you have a minus mg, so your weight force is negative 1.13886 newtons. And then, negative times negative is positive, so you have all positives in there. And then the height, or the y value, is 1.1 meters. And when you calculate that out, it comes out to 1.252. 746 Newton meters. Now, I wrote down all the digits, but then at the end of the calculation, you make your decision of how to round it off. So in this case, 1.253. All right? And so that's the way that I do it, and I recommend that to you as well. All right? Don't round off at every step. Round off at the last step if you can. All right? And if you're doing it on a calculator, you can do that. If you're doing it on pencil and paper, it might be a little bit more tedious, but you can still do it. All right? And notice that the GPE is 1.253, and automatically, since it's the halfway point, I know that at the halfway point, meter for meter, kinetic and potential are 50-50. All right? So make a note of that. If you drop it from kinetic energy 0 at any elevation, at half that elevation, the energy kinetic and the energy potential are 50-50. Just like Forrest Gump and Bubba Benjamin Blue. The Bubba Gump Shrimp Company. We'll just work it together, 50-50. Tell you what. All right, and that's what we got. We got GPE and kinetic energy, 50-50. Tell you what. All right? And just to reinforce, verify the hammer's speed value at 1.1 meters. Come on down. Don't be bashful, wherever you want to sit. You missed a bunch of clicking, but we still got some more clicking ahead. So, all right. Now, I want you to finish chapter 4, reading through chapter 4 and studying it. And I think I'll activate the chapter 4 mini review. And probably for exam 2, we're going to have the chapter 5 mini review because we're going to start chapter 5 today. All right, so here's the first part of chapter 5, angular momentum. And angular momentum is kind of an interesting concept. It is the rotational analog of linear momentum. P equals mv is linear momentum, or translational momentum, we call it. The momentum of going from point A to point B. The momentum of the hare and the tortoise. Going from the start of the race to the end of the race. Now, for something that's spinning or going in a circle, it doesn't actually go anywhere. It just keeps returning to the same point. But it still has some mv. And so the rotational analog for something spinning or on a circular path is called angular momentum, and we're going to start working on that today. All right, so before we do, though, let's go and review a few questions about centripetal acceleration, and so that we can kind of get to the idea of angular momentum. And we've already talked about centripetal acceleration, in terms of just general circles and circular motion, and we talked about satellites orbiting Earth and stuff like that, and we'll talk about some satellites now. But let's talk about cars on a racetrack. All right, so here's your question, and do the refresh key, because we're now going back to multiple choice. Okay, hit your refresh key or it won't work. Okay, driver X takes the track at a steady 88 miles per hour all the way through turn 1 and turn 2. Which turn requires greater centripetal acceleration? All right, think about that. Because those two turns are definitely different. I see people paging backwards in their notes. You're looking for the formula for centripetal acceleration, I bet. See, this is where having a notebook is pencil and paper. Think carefully and give me your answer. Centripetal acceleration. The Nardo ring. Now we don't have circles here, we just have parts, and they're not even perfect circular arcs. They're kind of straightening out and curving back. Twenty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, turn 2 is the correct answer. 50% of you got that correct. Shh. Now, here's the reasoning. You're going through at the same speed, right? 88. miles per hour. You're going to have to stay after class. Yeah. You're going to stay after class anyways, right? Anyways. So turn 2, here's the way to think about it. The turning radius. Turn 2, you could fit that's not a bad fit right there, at least for that part of the track. Pretty tight turning radius. Now turn 1, much bigger turning radius. And so if you just think of turning radii, you making a tight turn, you're going to feel it more in the car. You're going to be thrown to the side a little bit more if everything else is the same. 88 miles per hour. All right? Now, the formula, remember what the formula is for centripetal acceleration? V squared over R. No, not V squared over R squared. V squared over R to the first power. All right, next question. Scaredy Cat Joe. Now, he's on the same track. But he's a kitty cat, so he only goes at 9 miles an hour. And you can tell he's a scaredy cat because his hair is standing up on end. No. Where? Where do you think a typo? His centripetal acceleration in turn 1 is blah, blah, blah. The centripetal acceleration on driver X's car, 88 miles per hour run through. Make sense? Okay. Yeah, I see. I could probably reword that a little bit. Okay, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Yeah, you guys did good. It's turn 1, so the answer is less than. So Scaredy Cat Joe doesn't need as much grip on his tires or his toes as driver X because he's going slower. And here's the way that you would answer that. His V is smaller, so his V squared over R1 is smaller. You know, driver X has R1 in the denominator, but he has 88 miles per hour in his numerator, and it's quantity squared. Versus Scaredy Cat Joe's is about 10 times smaller, 9 miles per hour. So driver X has got about 100 times more acceleration at that speed. So his tires have to be 100 times more gripping than Scaredy Cat Joe. All right. Now, we studied centripetal acceleration, and then we applied it to gravitational orbits and stuff. We talked about, galaxies and stuff, spacecraft. Let's get back to that. We had a single equation that allowed us to connect orbital speed and central mass, in other words, the mass of the planet, and the orbital size. And here's the equation, gm over r equals v squared. Now, that's not a force equation because it's gm over r. It's not an energy equation because it's gm over r. It's a v squared equation, so it's kind of a... But that's what it is. That allows us to figure out the relationship between orbital size and orbital speed. Or, if we want, orbital period and orbital size. So the orbital period on a circular orbit anyways is 2 pi r, 2 pi times the radius, divided by the orbital period, capital T. All right. So if you specify specifying the orbital period is just as effective as specifying the orbital speed. All right. And there's times when we want to do that. The other way is to specify the orbital distance, r, and figure out the orbital speed. All right, so the examples that we talked about were, for instance, like a low Earth orbit spy satellite, where you specify the r, good and low, and you compute v. So, for instance, a typical spy satellite type orbit might be up at an altitude of 180 miles. All right, and that's a little bit below the space shuttle. They're about 200 miles usually, and the space station is, I think, is a little bit above that, and then the Hubble's a little bit above that, but they're still pretty close. They're still low Earth orbit. It's about 6,700 kilometers. Now, a student asked me, Dr. B, what's the difference between radius r and altitude? Altitude is measured from the surface of the Earth. So that's what NASA is going to talk about. But really, they're working with orbital radius r, and that's measured from the center of the Earth. All right. So the rocket, to get something up at this orbit, low Earth orbit, 180 miles, you've got to have a speed of about 17,000 miles per hour. So they got to get rockets that'll get them up there. If they don't, it'll just come right back down and splash down in the ocean, and you lost your satellite, which happens, occasionally. That something goes wrong with their rocket. Now, the other example that I gave you was geosynchronous communication satellites. So on that, you specify the orbital period, 24 hours. And then from that, you compute the orbital distance, r. Okay, so for 24 hours, so in this equation up here, v equals 2 pi r over t, you put 24 hours, well, you convert 24 hours to so many seconds. It's a lot of seconds. And you put that in the denominator. And then you put 2 pi r up here, and you substitute it in here, and you figure out, V's got to be 6,900. And so the rocket has to boost the satellite. So you figure out what the orbital radii are. about 42,200 kilometers. Altitude 35,900. So that's about 6.62 Earth radii away. All right, so that's, so we talked about that. Now, here's a question for you. Which one, for each of these spacecraft, you're moving on a curved path. All right? And you're always, if it's a perfectly circular path, you're always coming back to the same point. So it's automatically a candidate for using angular momentum, the momentum of something that's either spinning or moving along a curved trajectory. Question?
Why is time in seconds and not hours and minutes?
Here?
Yeah.
Well, because we want to get meters per second. I mean, you could do, put 24 hours here, but then you have to convert to miles and stuff. So we're kind of mixing stuff here. I always go down to seconds and meters most of the time. But if you look something up, if you look up NASA's table of planetary data, they have things, because it's planetary, they have kilometers instead of meters. But all you got to do is add 3 zeros to whatever they have, and that's meters. So now here's a diagram. Here's a couple diagrams. Now, Leo. We're not talking about Leo DiCaprio. We're talking about low Earth orbit. Okay? And that black dashed line around the Earth that you see it? This is all in proportion. That's where the space shuttle is. It's barely out in space. In fact, the geosynchronous satellite way out here on the red circle looks down on the space shuttle and the space station. Hey, you guys are barely out in space. You want to go out in space? Come on up here. I'm 6.62 Earth radii away. And then here's another orbit that you can, some spy satellites have this kind of an orbit. Now, this one is useful because the fast part of the orbit is down here at perigee, the point of closest approach. Gravity is stronger down here near the Earth, so it's really whipping. But out here, gravity's much weaker, so it's just kind of poking along. So this part of the orbit out here, making the turn here at apogee, it might be a couple hours. All right? So if you have a satellite that you want to look down the same point every day for 2 hours, you position it so that its apogee is right over. So if you want to look at what's that guy's name? Vladimir Putin's back pocket at noon, this is your satellite. It's going to be up there looking down at Red Square every day at noon. Yeah, we got it. Or you want to measure some kind of, use ground penetrating radar to look at, some, tank emplacement in Western Russia, see if they're preparing to invade Ukraine or Poland. They'll put something up there and they'll look down every day, twice a day, and they'll loiter. This is the part of the orbit where it's loitering. So it's going to be in motion, but they can change the camera angle slowly at that point. Now down here, they can do the same thing. It's in close, but they have to change the camera angle really rapidly. So, you have different applications for that. Anyways, all these are built for using the concept of angular momentum. Now, here's another concept that we want to talk about, and that is torque. Where you apply the force on something that can spin or rotate. Now, the good example is Rachel coming through the door in the back. Howdy, Rachel. Now, she just came in the back door, and you ever notice, I mean, you go by through doors all the time. Look at this door up here, okay? The hand plate is over there on the far left of the door. The hinge is on the right. Matter of fact, if you don't believe me, I'll just go over there and open it. Let me get my, cramp in my leg here. All right. I'll just push the door. Would you push the door open from here? No. You could. I mean, I could do it, but much better because the hinge is right here on the right side. So even a little shrimpy first grader can open the door here, but a little shrimpy first grader, not so much over here. So where you push from is going to control how well you can spin the door around that particular axis. Same thing on a teeter-totter up here. Sitting in this chair for 3 hours gets get cramp. So the same thing. Now this is a diagram from the textbook, and unfortunately, Great River Learning does not have page numbers in it. But in the first few screens worth of chapter 5, you'll see this one. And this is the one where the little girl, the daughter, defeats the son. The daughter's over here at point X, and she has a smaller weight force. So her point of application is further out on the seesaw. And here's the son. He's got a bigger weight force, but he's also closer in. Now, if the daughter were over here at point R on the right side, the same distance that point L is to the left, she'd be stranded up in the air. Because same distance is left and right, the one with more weight force wins. But if she poses out a little bit, she can win, all right, because she has more torque. And so those are, and we're going to be talking more about that on Tuesday. Now, angular momentum. Let's talk a little bit about this. As I already mentioned, it's a special kind of momentum for something that's not really going from point A to point B. It's going around in a circle, the object that is behind itself. The ice skaters at the Olympics have a great, you can see a great example of angular momentum. And actually, hey, you guys, conservation of angular momentum. That's what you see at the Olympics with the ice skaters. Because everybody knows, when they have their hands out like this and they're spinning, out on the ice, they're spinning at a certain rate. But as soon as they bring their arms in close, they really spin fast. Okay, that's the ice skater effect. And if they want to slow down again, they extend their arms. Or in the case of this young lady, they get on one foot and extend their leg and their arms out. And she's slowing down. Her center of mass is right above the skate. Okay? And so she's extending her leg and her arm on one skate and slowing down. Okay, bicycle wheels, same thing. Spinning. It's not going from point A to point. I mean, we could, and on Tuesday we're going to have a bicycle wheel in here, and you'll see how those work. But it has an axle, and if you think about it, every centimeter along the rim has a certain amount of mass. Okay, so you could pixelate the tire into pixels of mass arranged in a circular array. And they have some speed, however fast you get the bicycle wheel going. And so they have some momentum, but the thing is, it's not momentum from point A to point B so much as oriented to the axle. So the spin axis the spin axis is everything with angular momentum. All right, you have to, and a bicycle wheel has a natural spin axis. The ice skater has a natural spin axis. It's the line from her center of mass down through her feet to the ice, straight line. That's her natural spin axis. Everybody in this room, if you were out in space, in a spacesuit, and you weren't tethered in, and I gave you a push on your feet, you'd start spinning. Your feet would go back, your head would come down to the front, and you'd go spinning end over end. All right? And but the axis of rotation would go right through your belly button, basically. Everybody, the center of mass is right about your belly button. Plus or minus an inch or so, depending. Somebody with big feet is going to have a little bit lower. Somebody with a big head is going to have it a little bit above the belly button. But, women and men, it's just about that's why the belly button is where it is. So that when you're, before you're born, you're floating around in your mom's tummy, and the umbilical cord attaches there where it's going to cause the least amount of torque on you. And so that's why nature puts the belly button right where it is, right about your center of mass. So this is the whole idea of angular momentum, the momentum that's associated with spinning. Now, we're going to do some examples. We're going to talk about angular momentum, the conservation of angular momentum, and you can read about it in chapter 5. Conservation of angular momentum is why the ice skater, here's another ice skater. It is why the ice skater effect works. Why is it that bringing your arms in speeds up your spin rate? And and it's not just ice skaters. It's not something cool for the Olympics, but it's boring otherwise. Yeah, when you have a supernova explosion of a gigantic star, and you form a neutron star from the leftovers, or a black hole, it's going to conserve angular momentum. But because it's so compressed, the neutron star or the black hole, the spin rate is going to go through the roof. And we have things the size of the number of kilograms of the sun, the mass of the sun, that take like less than a second to spin 360 degrees. And we see zillions of them. Neutron stars, we call them. And if you've ever heard the word pulsar, there's things called millisecond pulsars. That means they spin on the order of a few hundred or 1,000 times per second. And they're about the same mass as the sun. They're just extremely... You know what they're the size of? They're the size of Orange County. They're really small. A lot of mass, really small, and boy, do they spin. So it's, conservation of angular momentum. It's not just for the Olympics, lovely as they are, the ice skaters. Now, I'm going to ask one more clicker question. You guys got to catch up by one question. Let's do one more. And this is going to be, and it's not on the screen, so it's going to be verbal. And so my question to you is, vote A for yes, B for no, and then hit the send key. And my question is, do you want to dismiss early today? A for yes, B for no. Well, 2 people voted no. Okay, that's it. We got to stay. All right. Anyways, you're dismissed. But do cast your vote, because boy, that was the fastest 200 votes I ever saw. Woo, doggies. All right, see you guys on Tuesday. Read chapter 5. I tell you what, always something.